Hello. In today's lab, we will work with two types of pendulums that we talked about in the theory class. The first type of pendulum we will work with is the simple pendulum. Now here I have a simple pendulum. This is the pendulum bob, and the length of the pendulum is from the support to the center of the bob. Now, do you recall the equation for the period of oscillation of a simple pendulum? Well, I'm sure you can recall that. The period of oscillation of a simple pendulum T is 2 pi square root of L over G, where L is the length of the pendulum and G is the acceleration due to gravity. What is one oscillation? This is similar to the experiment you did with the springs. Now, if the bob is at one extreme, the time taken for it to go to the other extreme and back is one oscillation. So if I set it into oscillation, you can measure the time for 10 oscillations. So start the clock. Well, let me set it oscillation. Start the clock when the pendulum is at one extreme, and then say you start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you are. You can measure the time for 10 oscillations, and hence you can calculate the period by dividing that time by 10. Now, what are the variables here? We will change the length of the pendulum. The length of the pendulum can be changed. You can see I have got a big length here. I can change the length of the pendulum by any amount. So that will be one variable. We'll change the length of the pendulum, and of course when you change the length, the period will change. G is a constant. So can you now write this equation in the form y equal to mx? In every lab, I will be asking you to do that. First of all, let's write this taking away the square root. We get t squared equal to 4 pi squared times L over G. And that can be rewritten as t squared equal to 4 pi squared over G times L. So you draw a graph of t squared on the vertical axis and L on the horizontal axis, right? The slope of that graph will be 4 pi squared over G. So once you measure the slope, you can use that value to obtain a value for acceleration due to gravity. That is your first lab. And make your tables neatly as I have given you in the manuals. Always remember, before you start a lab, read the manual carefully. Alright? And I will set up the pendulum for different lengths, and I have given you the different lengths I'm going to set up. I'm going to start with 10 centimeter, then I will increase the length to, do you remember, to 20 centimeter, to 30 centimeter, all the way to 1 meter. Okay, ready? Now to begin with, you need to have your stopwatch on your video. So if the stopwatch is not there, minimize the video, and then get the stopwatch and get the stopwatch on the video so that you're ready to measure the period. I have now set up the pendulum with a length of 10 centimeter, and I'm going to set it into oscillation, and I hope you know how to find the period. Now keep a reference point somewhere. You can do that on your own, and then when the bob comes over there, start your clock and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop the clock. That is the time for 10 oscillation. Okay, and we will do 3 trials for each length. Alright, and I will give you those 3 trials for each length. Let's go. Start. You can start anytime. Remember, you don't need to start the clock as soon as I let it go. You can leisurely start whenever you want. Alright, I'm going to let it oscillate. Alright, I hope you got 1 trial there. Second trial, measure the time for 10 oscillations. Alright, let's do a third trial for this length. Okay, you have now 3 trials. You have measured the time for 10 oscillations 3 times. Find the average of that, then divide the average by 10, and that is the period for this length. I'm now going to increase the length to 20 centimeter. The length of the pendulum now is 20 centimeter, and do the first trial. Alright, I hope you got 10 oscillations there. Let's do a second trial for the same length. Start your clock when you are ready. Okay, let's do a third trial. All right. Okay, you have now 3 trials for 20 centimeter. Find the period for that length. Now the length of the pendulum is 30 centimeter, and let's take the first trial. All right. If you want a reference point, I can provide that. Okay, let's take a second trial there. Let's now do a third trial for 30 centimeter. Okay. I'm sure you have now. The time for 3 trials, find the average and divide by 10 to get the period. I have now the length of the pendulum increased to 40 centimeter, and let's take the first trial. Okay, I'm going to give you a second trial now. Measure the time for 10 oscillations. All right, I'm now going to give you a third trial on that length. All right, now you got 3 trials, find the average, and from that find the period of this pendulum. I have now changed the length of the pendulum to 50 centimeter, and let's do the first trial. Okay. Okay, a second trial for 50 centimeter. Okay, now let's take a third trial for 50 centimeter. All right. All right, find the period for that length. Now the length of the pendulum is 60 centimeter, and let's do the first trial. Alright, a second trial for a length of 60 centimeter. There we go. Okay, a third trial for a length of 60 centimeter. Okay, let's now change the length to 70 centimeter. Now the length is 70 centimeter and let's do the first trial. Okay, now the second trial for 70 centimeter. Let's now do a third trial for 17 centimeter. So you have now 3 trials for a length of 70 centimeter. Find the period for that length. Now the length of the pendulum is 80 centimeter and don't let the clamp disturb you. Just concentrate in here. Let's do the first trial. Alright. Measure the time for 10 oscillations. Okay, let's do a second trial. And now the third trial for 80 centimeter. Okay, there you go. Alright, I hope you got 3 trials for that and measure the period for that length. I have now the length of the pendulum changed to 90 centimeter, and I'm going to use very small amplitude here. So use the edge of the table as your reference point. Alright, let's do trial 1. Okay, let's do a second trial for length 90 centimeter. Okay. Alright, you have now 3 trials for a length of 90 centimeter, and let's go to the last one, 1 meter or 100 centimeter. I have now the length of the pendulum 100 centimeter or 1 meter. Again, use the edge of the table as your reference. Take the first trial. Okay, let's do the second trial. Alright, let's do a third trial for 100 centimeter. There we go. the trial. We will now discuss the second type of pendulum called the physical pendulum. What is a physical pendulum? Anything like a meter rule pivoted from a point and set into oscillation about an axis passing through that pivot is a physical pendulum. Now, I can set up a physical pendulum just using the same setup. Now, first of all, I need to find the center of mass of the ruler. And the center of mass of the ruler that we're going to use is at the 50 centimeter mark. And then we will choose the pivot point at distances 5 centimeter. So we will pivot the meter ruler at D, the uppercase D equal to 5 centimeter, 10 centimeter, 15 centimeter, and so on. And here I am using the pivot point so that the pivot point is 5 centimeter from the center of gravity. This is the center of mass, and that's the pivot point. And the axis of rotation, if you now rotate the meter rule, it will be rotating about this horizontal axis. That means this has a moment of inertia. I hope you understand these terms. It has a moment of inertia I about the axis of rotation. Alright? And we set it into oscillation like this. Can you see it oscillating? It's oscillating back and forth. And we will measure the period of this oscillation. Now, does anybody recall the equation for the period of oscillation of a physical pendulum? The period of oscillation of a physical pendulum is, I'm going to write it over here, is T equal to 2 pi square root of I divided by mgd, where I is the moment of inertia of this ruler about the axis of rotation, about this axis. And m is the mass of the ruler, d is the distance of this axis from the center of mass, and at this moment that distance is 5 centimeter. Alright, we will repeat it for 10, 15 and so on. So the period of oscillation of a physical pendulum is 2 pi square root I divided by mgd. Can you represent this I, moment of inertia of the ruler about this axis? Can you represent that I in terms of the moment of inertia about its center of mass? Well, you know that the moment of inertia of an object about any axis is the moment of inertia about its center of mass plus md squared. This is called the parallel axis theorem. In other words, if this is an object and this is the center of mass, here is the axis that passes through the center of mass. If you now want to find the moment of inertia I about this axis, this is the distance d, the distance of the axis from the axis that passes through the center of mass. That is your d. So, moment of inertia I about any axis like this is moment of inertia of that about an axis through the center of mass plus md squared, where m is the mass of the object and d is the distance of this axis from the center of mass. So I'm going to replace that I by this quantity, and let's see what we get. We now have the equation, the period of a physical pendulum like this is 2 pi square root I center of mass. I center of mass stands for the moment of inertia of the meter ruler about an axis through its center of mass, plus md squared over mgd. Now, here d is the variable. We are going to change d. The first value of d is 5 centimeter, then we go to 10, 15, 20, and so on. Now, for each d, we will measure the period. Now, you will see when you measure this, as you increase d, the period is going to decrease. And it is going to reach a minimum, and thereafter it is going to increase. So, if you plot a graph of t squared on the y-axis, let's see if you can see that. I'm going to move this out. If you plot a graph of t squared on the y-axis and d on the x-axis, the graph you will get will be something like this. So, as d increases, the period will decrease, reaches a minimum, and thereafter it will increase. Now, I want you to obtain the value of d that correspond to the minimum period. In order to do that, all we need to do is draw a tangent to this curve and see where it touches the curve, and then draw a vertical line to the x-axis. This will be then called the d minimum. What does d minimum stands for? D minimum stands for the value of d corresponding to the minimum period. So you will draw a graph of t squared on the y-axis and d on the x-axis, and from the graph measure this value, the value of d corresponding to the minimum period, and we call that d minimum. And I have worked out the mathematics of it, and I have given you an equation here that d minimum equal to, what is that equal to? Square root of I center of mass divided by m. So once you measure this quantity d minimum, and knowing the mass of the meter rule, you will measure that, you can calculate a value for I center of mass for the ruler, the moment of inertia of the ruler about its center of mass. That is the objective for the second part of this experiment. So measure I center of mass experimentally. You can also obtain a theoretical value for I center of mass. You see, if you remember the lecture classes we did on Physics 1, the moment of inertia of an object like a meter ruler, the moment of inertia of an object like this will be about its center of mass, will be 1/12 ml squared. And in this case, L is the length, which is 1 meter. So when L equal to 1, that will be 1/12 of m. So I center of mass will be 1/12 of m. I don't think you can see that. Well, you don't need, I can write it over here. 1/12 of m. So let's start by measuring the mass of this. Alright, I hope you understood the theory behind it. This is the theoretical background. Okay. Alright, I want you to measure the mass of the ruler that we will be using in this experiment. And here it is. Measure this and note it as uppercase M. The mass of the ruler equal to this, and its center of mass is at the 50 centimeter mark. Okay. I have now set up the physical pendulum so that the distance uppercase D is 5 centimeter. Alright, I'm going to set it into oscillation, and this time you may not get 10 oscillations. So I want you to measure the time for 5 oscillations, and we will do 3 trials. Alright, and I will keep my finger as a reference, and let's go. Measure the time for 5 oscillations. Well, you can barely get 5. Alright, let's do a second trial. Okay, let's do a third trial. Alright, I hope you got the time for 5 oscillations for 3 trials. I'm now going to change the distance D to 10 centimeter. Alright, the distance D is now 10 centimeter. Let's do the first trial and measure the time for 5 oscillations. Okay, let's go. Well, we've barely got 5. Let's do a second trial. I think I need to give you some more trials. Let's see how many you can get. 5. Let's see here. One more. Well, that's good actually. It's still oscillating. You can measure that time. Alright, let's do one more trial. Alright, I'm going to give you one more trial so that you can take the best 3 you have. There we go. Okay, so you have 3 trials for a distance D equal to 10 centimeter. I have now changed the distance D to 15 centimeter. Let's do our first trial. Measure the time for 5 oscillations. Okay, let's do a second trial to measure the time for 5 oscillations. All right, that was good. Let's do a third trial. So you have now 3 trials for the time for 5 oscillations for a distance d equal to 15 centimeter. Let's now change that to 20 centimeter. I have now changed the distance d to 20 centimeter, and let's do the first trial. Well, I think they're very enough for you to get 10 trials. Well, 5 oscillations there. Let's do a second trial. All right, now a third trial. Okay, we will now change the distance d to 25 centimeter. I have now the distance d at 25 centimeter, and let's measure the time for 5 oscillations. The first trial. All right, let's do a second trial for that d equal to, what's the value there? 25 centimeter, is that right? Okay, the third trial. All right, you see the illusion the light is playing on you. This is not a bend on the ruler. The ruler is straight, so don't worry about that. I have now changed the distance d to 30 centimeter? Is that right? Well, let me make sure. I'll be 5, 10, 15, 20, 25, 30 centimeter. D is now 30 centimeter, and let's do the first trial. Alright, let's take a second trial. I hope you understand one oscillation is one complete back and forth. Alright, the second trial for D equal to 30 centimeter. Alright, now the third trial for D equal to 30 centimeter. There it goes. Alright, remember you need to measure these times at least up to 2 decimal places. Okay, let's now change the distance D to 35 centimeter. I have now the distance D equal to 35 centimeter, and let's take the first trial. Measure the time for 5 oscillations. Okay, let's do a second trial. Okay, now a third trial. Alright, we have now 3 trials for D equal to 35 centimeter, and find the period of oscillation there. I have now distance D equal to 40 centimeter, and let's do the first trial. Okay, let's do a second trial for D equal to 40 centimeter. There you go. Okay, a third trial for D equal to 40 centimeter. Ready? I'm sure you got 3 trials for that distance D equal to 40 centimeter. I have now the distance D equal to 45 centimeter, and let's take the first trial. Alright, let's do a second trial for D equal to 45 centimeter. There we go. Now a third trial for D equal to 45 centimeter. Alright, we now have the complete set of data for this experiment. As I told you earlier, plot a graph of T squared against D and find the value of D that correspond to the minimum period and use that value of D in this equation to obtain the value of the moment of inertia of the ruler about its center of mass. And this is the theoretical value. Alright, now obtain the percent error between the actual value and the experimental value. Now answer all the questions and prepare your report and upload it onto the assessment draft box. Alright, you got any questions? Get back to me and I will answer all your questions. Alright, I'll see you for the next lab later on.